Okay, today we are talking about separable differential equations. And I know the title of this section is actually called Exponential Growth and Decay. We'll get to that part in tomorrow's PowerPoint video. But this one I wanted to cover separately and show you some examples. So a separable differential equation can be expressed as the product of a function of x and a function of y. So you have two different functions that you're dealing with. H of y can't be 0. You'll see this in an example. So suppose you have dy dx equals 2xy squared. So notice we've got a function in terms of x, and we have a function in terms of in terms of y. So what you're going to do is you're going to separate. You're going to put the dy with the y and the dx with the x's. The dy and the dx can never be in the denominator, so you're going to multiply both sides by dx and divide both sides by y squared, which is why our h of y can never be 0, because this y squared can't be 0 because we're dividing by that. So you end up with this. So we have dy over y squared, and we're going to have 2x dx. So again, you just separate to the both sides. So you have the y's on one side with the dy, the x with the dx on the other side. Then what you're going to do is you're going to integrate both sides. Well, they changed that first. So remember, with solving equations, whatever you do to one side, you have to do to the other. That applies to differential equations. So we can actually integrate both sides. So that's what we do next. We integrate both sides. So then these are fairly straightforward with the power rule in reverse. So when you integrate both sides, you get this. Notice you have a constant because they are indefinite integrals. So we have this C1 and C2, they've labeled them. But these are just kind of arbitrary constants. So what you'll see done instead is a combined constant of integration. So typically when I go through and do these, I actually don't even do this step right here, because I just go right from here to here, and again, that's called a combined constant of integration. So, oops, now what have I done here? So then all they did here was some algebra, so solving for y, when you do that. So you solve for y, and then you would have that, and you would be done. I'm going to show you some examples where we're actually going to solve for the constant, because we're going to be given an initial value problem, but these don't do that here. So we end up with y equals and this quantity here. Okay, here's another example. So you're going to separate it out first. So the y, the expression in the parentheses with the y is going to go to the left side, so we're dividing by that, and then we're multiplying both sides by dx. So we end up with this. We integrate both sides. On the right side, you're going to do a u substitution. So all those other things we learned still apply. So if you let u equal x squared, then you end up with du equals 2x dx. So we have everything there in place. Now the left side of the equation, you would just need to know that that was the integral for inverse, or that, and when you integrate that, you get inverse tangent. Again, I would do the combined constant of integration. You get e to the u when you evaluate that integral, and don't forget to put the x squared back in there, and then combine the constant of integration. Now, at this point right here, this is called an implicit equation. So we solved it implicitly, an implicit function, but we want an explicit function. So one of the things you're going to see when I show you some examples and we actually solve for the constant, this is the step where I actually put the values in when I have an implicit function, and then we would solve for c at that point. And then now we're actually going to find the explicit function by solving for y, so we do the tangent of both sides. And when you take tangent of an inverse tangent, then you're just left with y. So we end up with this. So that would be our solution for the differential equation, and we did that by separating variables. You can't factor out the constant. Remember, you can't distribute tangent. Remember not to do that. So that's just kind of an overview of the lesson. But what I want to show you now is some examples. So we're going to take a look at those. So we're being asked to solve the initial value problem, so this is a little different. And then we are also going to talk about the domain, if there's any restrictions that we have to worry about. So the first thing I'm going to do on this problem is I'm going to, now this time the y is already in the denominator, so I'm going to move the y to this side, so I'm going to multiply by y, so I get y dy, and multiply by dx, I get negative x dx. This is going to be for later so that we can solve when we get to that part. So now I'm going to integrate both sides. Here, power rule in reverse, so I get y squared over 2 equals, here I'm going to have negative x squared over 2 plus a constant. So notice how I just did the combined constant of integration. So it's an arbitrary constant, so you don't have to put a constant on both sides. You can just do it like this. So this is going to be the step where I substitute the value x equals 4 and y equals 3. Just trust me, it's a whole lot easier to do that. So I'm going to substitute those values in, and when I do, I get 9 halves equals negative 16 halves plus c. So c is 25 halves. So now I'm going to come back over here and go on with my problem. Okay, and I'm going to, this is a 2 right here, not a very good one. And so I'm going to use fraction busters, cancel out that. So I get y squared equals negative x squared plus 25. So that means y is the square root of, and I'm going to put the 25 first. Now, by the way, this part right here, if we had rewritten this, x squared plus y squared equals 25, this is a circle with a radius of 5 centered at the origin, okay? So when I square root it, this is a semicircle, still centered at the origin. And how do I know if it's the top half of the circle or the bottom half of the circle? Well, we were given the point 4, 3 as being on our function, as being a solution to the function. So that makes it the top half of the circle. So we end up with this. So on this particular problem, we are actually, so this would be my answer. And then I need to consider any potential domain restrictions. And notice that we can't, this 25 minus x squared has to be greater than 0. And the reason I say greater than 0 and not equal to, because you might look at that and say, well, you can take the square root of 0. But originally our problem had y in the denominator, so y can't be 0. So 25 minus x squared has to be greater than 0. And you can actually, let's kind of, here I get x squared is, if I move it to the other side, we'll have x squared is less than 25. So x squared minus 25 is less than 0. So think about the graph. If you took the parent graph and moved it down 25, it's going to look something like this. It's going to open up. I'm just kind of going back to what we know about parabolas. So it's negative in between the intercepts. The intercepts are going to end up being negative 5 and 5. So our domain for which this is valid is between negative 5 and 5. So you do have to think about certain situations, like if you have a square root, you have to make sure that the radicand is greater than or equal to 0, and in this case it couldn't be 0 because of our original problem. Things like if you have a natural log, you have to make sure that it's not, you're not taking the log of a negative or 0. So things like that that you have to think about when those situations arise. So this part here would be our answer. Okay, on the next problem, we're going to start off by separating. So I'm going to have, I'm going to bring this and think of it as 1 over y dy, or I could have put dy over y, equals 2x dx. So that's my separating part, okay? Next step, integrate both sides, okay? Now think about the derivative of what will give you 1 over y. Well, that's going to be ln y. And you might wonder, how come I use absolute value? Y can be negative here. It's possible y could be negative, but it can't be negative here. So I'm using absolute value to make sure I don't have a domain issue with natural log. So over here I get x squared, because that would be the antiderivative, and then I put my arbitrary constant plus a constant. Now this is an implicit function. Now is when I'm going to plug in the point 0, 3. So when x is 0, y is 3. So I get ln 3 and plug in a 0. So that means my constant is ln 3. I don't need the absolute value because 3 is positive. So that's my constant. So now I go back to my equation, my implicit. Okay, and now I need to solve for y. So I have to think about, how do I undo natural log? Well, to undo natural log, you're going to exponentiate both sides with a base of e. Well, that cancels out these and leaves me y. Actually, I'll leave it like this for a minute. This is the tricky part. So off to the side, and you might wonder what why I'm doing this, but if you remember something like x squared times x cubed equals, remember when you multiply and the bases are the same, you actually add the exponents, 2 plus 3. Or we would say x to the 5th. Well, we're going to do this backwards. Like here, I could have said, if I had x to the 2 plus 3, I could have said that was x squared times x cubed. So right here, I have e to the x squared plus ln 3. So I can say that's e to the x squared times e to the ln 3. Okay, so think about that for a minute, because what I'm doing, or go the other way, I'm multiplying and the bases are the same, so I add the exponents, and that's exactly what we did there. So now I can evaluate this. So this I'm just going to leave, e to the x squared, but e to the ln cancels out and just leaves me a 3. Now also, e raised to a power is always positive. So this is always positive. And since it's always positive, I don't have this issue with the absolute value of y over here. So I can just say y equals, I'm going to put the 3 in front, and this would be my answer. And this is valid for all real numbers because we don't have any restrictions on this function at all. Okay, so that's how you would do one like that. So again, I want to point out that when I plug in the given values to solve the initial value part, I always do that when I have the implicit equation before I solve the explicit. I just find that the algebra is much easier if you do it that way. Okay, next problem. We've got, again, this one's a little bit tricky. Because you might look at this and say, well, there's nothing to use for x. There's only a y. Let's just put a 1 here and say that this is 1 times cosine squared y. So I'm going to divide each side by cosine squared y. So that's going to put a 1 over cosine squared y here, dy. And I'm going to have a 1 dx over here. Okay? Now I'm actually going to change this. 1 over cosine squared is the same as secant squared. And now I'm ready to integrate both sides. So recall that the derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. And the derivative here is just x, or the antiderivative. Notice that if I take the derivative of x with respect to x, I get 1. Okay, so then we have plus a constant. Now I plug in my 0 and my 0. So I get tangent 0 equals 0 plus c. Tangent of 0 is 0. So my constant is 0. So I just have tangent y equals x. And now I want to undo tangent, so I do inverse tangent. So if you do inverse tangent of both sides, we get y equals inverse tangent of x. And this one is not going to have any restrictions, so this is also all real numbers. Okay, one more that I want to go over. So on this one, again, notice that I have e raised to, and I have a difference here. So recall that if I had, let's say x to the 5th over x squared, that we could, and so we would subtract the exponents, and normally we would go this way, and now we're just going the other way. So I can think of this as, so I'm going to rewrite this as dy dx equals e to the x divided by e to the y. Okay, so next we're going to separate the variables, and I'm going to get e to the y dy equals e to the x dx. Now I'm ready to integrate both sides. So if you do the antiderivative of e to the y, you get e to the y. And here we get e to the x plus a constant. Now I'm going to plug in my values. So when x is 0, y is 2. So I get e squared equals e to the 0 plus a constant. Remember that e to the 0, anything to the 0 power is 1. So we get c equals e squared minus 1. E is just a number, but we're going to leave it e squared minus 1 because then it's exact. So next, we are going to go back to our equation here where we had e to the y equals e to the x plus the constant was e squared minus 1. And now I need to undo having e to a power. So to undo that, the inverse of that, of exponentiating with a base of e, is to take the natural log of both sides, but you're taking the natural log of that whole thing, so that when you do that, we now have y on this side equals ln e to the x plus e squared minus 1. And this one, remember I said that sometimes you have to think about any restrictions, and this is natural log, so we would need to make sure that this wasn't negative. But you can kind of confirm e squared is 7 point something. So you can confirm that on your calculator. And since e to the x is always positive, and then if you add 7 point something to that and subtract 1, this whole thing is always positive. And so since this is always positive, we don't have a restriction, so it's all reals. But this is our solution that we were looking for. Okay, so that should help you. You only that should actually, the homework that's for this, you won't have till tomorrow. You'll have a few problems like this to do. Your assignment that's due tomorrow is just the quick review. So anyway, so that should help get you ready for that.